Alright, so I have the game project set up. I mostly just copied all the files from previous projects I've done, like I previously did an HTML5 game, Call of Birdie. So a lot of this code, like the gl.js, is like a WebGL 1 wrapper. I wrote this years ago, and I've just reused a lot of this code over the years on projects. It does a lot of standard stuff you see in other engines, where it just encapsulates like the OpenGL features into a class called like render texture, and that all handles the frame buffer and texture behind the scenes. And there's other stuff like that, like shader class, mesh class. So anyways, this code's all documented because I wrote this years ago. None of the other code I'm going to write for the game is going to be documented because it's just like, why? So I have a bunch of the game set up. You can see here in the game I have fruit definition, that this defines the sprite sheet positions of the fruit. To do this, I just went into the sprite sheet image in Paint, and I just drew bounding boxes over everything and just wrote down the exact pixel positions of the boxes. So I just sort of did all that by hand. And here's the app when I open it up. You can see I have a basic UI set up and a background. This background is going to be the actual like game field. The fruits will drop inside this cup you can see here. And these are just buttons styled with CSS. The title is made in paint.net. This is just a mock-up. I'm going to change this once I have some actual like art to go in the background here. These buttons I'm probably gonna, I think I might adjust the colors and things of these, but it's just it looks pretty good so far, I think. So the next thing I need to do that I'm working on is rendering the fruit, and to do that we're gonna render the fruit as a single mesh, batch all the fruit together into a single mesh so we can just render them all because they're in the same sprite sheet. And right here we render the sprite sheet when the game opens up, and that's that. So that's what we just did in our shaders.glsl here. You can see our fruit sprite sheet shader. That's all of that code for the art that we just wrote. And so it just runs this once when you open up the game, renders it to a sprite sheet, and then when it actually is when you're actually playing the game, it's just sampling the texture and just running this really simple shader. I do think these procedural shaders would actually be, they would be probably too complex for some mobile devices, or I don't know if I want to say too complex, but like it's a lot slower than just sampling from a texture. So why not just sample from a texture, and then you also get the benefits of mapping and anti-aliasing. So you can see here some of the standard stuff we have where we resize the aspect ratio to make sure that the game field stays fit. You can see it all stays, so you can always see the whole box, the whole playing field. Alright, so let's get to writing this rendering code. Alright. Here I have the fruit rendering set up. These are all being rendered as a single mesh. If we go to the rendering code right here, so we can see we allocate the vertex and index buffers. Since it's just all quads, we can actually do constant indices that are only updated once when we allocate the buffer. So then we build the mesh vertices every frame. So we build the vertex positions and atlas UVs to build the quads to render each of the sprites. This isn't completely done. I haven't put in rotation yet, but it has aspect scaling, and it's pretty much done. And then we just update that and render it. So then I've started doing the physics engine, and so the next thing I'm going to do is I'm going to be going through each of the shapes and creating the collider primitive shapes that match up with the art. So I've started programming the collider. These are just defined as polygons made of points that are either connected in a closed polygon or just like a wiggly line like a rope. So then what I've been testing is calculating the center of mass. I was pretty sure you could do this by calculating the center of each line and then weighting it by the line length, but I wasn't sure, so I actually did the more complicated or unoptimized version of integrating across each line, and it does come out with the same result. So this does work. So I can actually show this here in the console. You can see this is the optimized weighted center of each line. I think this is actually called the centroid as well, not just center of mass. So we need 0.666 and 0.8333. And then, so if we go to the integration here, so this is an approximation because we only integrate to a precision. So this gives us the same thing, or pretty much the same thing, 0.666 and 0.83, but to the precision of 0.01. And so we can see it gives the same result, so we can use this optimized version. It is the same thing. It's actually more accurate because we're not to the precision of the integration. Alright, I have the main code for the collider collision set up now. So this function nearest returns the distance and normal to the nearest point on the collider. So given this xy point relative to the collider, we get the distance and normal, so you can multiply the normal by the distance, and that'll give us the offset of how to move this point to solve the collision against the collider. And so how this function works is as we went through before, our collider is made up of points forming lines. So our collider can either be closed or not closed. When it's closed, it fills in the inside of the polygons and connects the end point to the start point. If it's not closed, you can just consider the polygon a bunch of lines, like a rope. So when we have the polygon so to do the nearest point, we loop through all of the lines, and if it's closed, we find the maximum distance. If it's not closed, we find the nearest distance to the point. And when it's closed, to do the negative distance, we use the planar distance, because inside the shape, we don't need to do anything more than that. It can just be the planar distance there, and we also need the planar distance to check if it's inside the line. And so this uses I should actually mention this here, this uses a clockwise winding. The points need to be clockwise. Alright, so to show off how it describes the collider, we can see the array of points here. This is just describing a triangle, currently a closed triangle. So if alright, so here we have our triangle defined by those points, and this has 0 thickness, so this makes a sharp edge. If we add thickness, it makes the edges more rounded. And so this visualization here, I wrote this code that loops through and generates a canvas image visualizing the distance field of this nearest collider function, rendering the distance field as these repeating lines, coloring it green inside the shape and red outside. And this way we can debug the collider. The distance field needs to have these evenly. If the lines are distorted anywhere, it means the distance field is broken and my function isn't working properly. And it also is needed for, I'm going to be manually creating these colliders for each of the fruits. So just to show this off, I'll change this collider from closed to not closed, and we'll give it some thickness. Otherwise there won't be an inside of the shape. So here we can see now that it's not closed, it doesn't connect the end line to the beginning line, and the inside of the shape is just around the lines. And so this this requires the points to be defined in clockwise order when it's closed. So the one thing I'm not sure about this system that I need to test is whether or not this can support non-convex. So this is obviously when it's lines, it can be concave or non-convex, but when it's the closed polygon, I'm not sure. I believe the closed polygon, when it's concave, will have clipping issues, where when it goes out of the bound, like, I don't know how to describe it, when it extends out of the bounds of being convex, there'll be a clipping issue where it messes up the inside and the outside of the shape. I'm going to test that right now by making a concave mirror shape. Alright, well, I started working on a concave polygon and I noticed an issue with convex polygons. So this point right here looks like it is actually broken or breaking the distance field. And so thinking about this a bit, I think I was wrong about this. I said this is supposed to use the maximum distance. I think it's still supposed to use the minimum distance when it's positive distance, and it's supposed to use maximum when it's negative distance. And if you think about it as when it's positive distance, the minimum is the closest to the surface, and when it's inside, the maximum is the closest to the surface, because when it's negative, the maximum is actually closest to 0. So let's try this out by flipping this to negative. Okay, I think I need to debug this more. This looks pretty broken. Okay, so looking at this, I think I need to separate the internal and external distance, because I have to set the distance here to negative to do the max distance properly. Because imagine if you start at 1e16, nothing will ever be bigger than that. So I think what I need to do is I need to do an external distance for this, and then keep the internal distance here that starts at 1e16. And then the question is, how do I combine them down here? And how do I combine the normals? And so just as a test to make sure I was right, I've taken an unclosed polygon, and I look at this polygon now, and you can see what the proper distance function should look like here. So that, yeah, the other distance function was definitely broken. So we do need to fix this. Alright, I managed to fix it. It kind of threw me off. It was a little bit tricky. So I separated the distances, and originally I was doing what I did before, where I only calculated this max distance if the face was smaller than 0, so it was inside. But then I realized you actually had to check whether or not you use the internal or external distance is dependent on whether or not that final planar distance is here. Let me just show you what happens if you use the planar distance. So this is actually, wait, hold on, I need to change the scaling so it doesn't go through square root. So this is what a lot of tutorials do, or at least this is the way they represent polygons. It's just by splitting off the planes exactly. And this doesn't give you those same rounded edges I talked about. And as far as I'm aware, that actually isn't as good for collision detection. But this works, as you can see. This gives us the proper inside out of the polygon, and it does give you a relatively correct distance, except for at the edges here, where it keeps giving you the as you can see, it keeps being directed towards the plane. This is actually equivalent to, I believe, either Manhattan distance or absolute distance. I can't remember which one, but we want actual proper Euclidean distance. So when we are outside the shape, we want to use that distance function that uses our line distance that we calculate here. So that's why we calculate this separate external distance using the lines, and then switch that out when it's inside. And there we go. That gives us the proper distance function. So, okay. I still don't think the concave polygon is going to work, but let's try. We'll flip this 0.5 to negative 0.3, and I'll make this concave. And yeah, you can see it messed up. It's interesting. The outside distance function is actually correct, you can see here, but the internal distance function, it no longer works. And I understand this. It relies on the same concept as point and the point in polygon algorithm, where it's like the clockwise winding. If you add up all the angles, basically if it's concave, the angles no longer add up to 360, and the detection of when it's inside or outside the polygon no longer works. So the only concave shape I have is the banana, so I'm just gonna need to combine two convex colliders. It's just, I was trying to think if there was a way to get concave colliders to work. All right, we have I've finished the colliders. So here we have the pineapple. It's just represented by a circle collider. So if you see the small white line, that's the actual boundary of the surface of the collider. So if we go into the physics code here, I've defined all the colliders here. Some of them are just defined manually, writing out the points. Some other ones, like the line, watermelon, and banana, I actually generate the points using like sine and cosine, because the points are in arcs, so it's just easier that way. This way we could just generate the colliders. This actually didn't take too long. And before I was talking about the banana being concave, so I was able to just represent the concave issue was only if the polygon was closed. I was able to represent the banana with just like a unclosed line capsule polygon. The banana is probably the most approximated shape, like inaccurate to the actual art, but it's still really good, I think. So I'll just go through the shapes here. Here we have the blueberry, pretty small, but you can just see I'm pretty much, when I made these, I just try to match up the white line roughly to the black outline, or where the black outline starts. The black outline of the shapes is supposed to be the actual edge of the shape. Like the color is where the actual shape is supposed to end. So that's why I'm trying to line up the white. So you can see here the raspberry as well. I just did another circle. So these smaller shapes, I just approximated them with circles. And then the strawberry here is like a rounded triangle polygon. The lime here is the arc I just talked about. It's just like a halfway part of a circle. The kiwi is like a big fat capsule. You can see it's a bit longer on one side. The apple is like a square that's a bit less wide at the bottom. And then here's the banana capsule I talked about. So you can see here at the ends, the capsule sort of goes out away from the surface. So here I think it's okay because it's like sort of emulating the stem. But out here, yeah, like if any fruit goes against here, or if it like bounces along here, you'll be able to see that the banana is sort of like floating on an edge. I was thinking of changing this, maybe pushing the collider in a little bit. But I don't know, we'll see. That might be something I change when I actually get the game physics going. So then the mango is another sort of triangular rounded polygon. The watermelon is another partial circle, another arc. And then you saw the pineapple. So there we go, that's all the shapes. So now we can actually start doing the physics for the game and dropping these fruits into the bottle or jar.